Today, we're diving into what is, without a doubt, the single most important algorithm in all of modern AI. Seriously, it's the engine that lets neural networks actually learn from their mistakes, and it powers pretty much everything from the camera on your phone to the biggest, most powerful language models out there. It's called backpropagation.
So what does that really mean, to learn from a mistake? Well, it really all boils down to this one simple question. When an AI gets something wrong, like say it sees a picture of a cat and calls it a dog, how does it tweak its own internal wiring so it's less likely to make that exact same mistake again?
You see, the whole learning process gets kicked off by failure. Yep, it starts with a mistake. When a neural network gets an answer wrong, it calculates an error value, which is often called a cost. And the bigger the screw-up, the higher the cost. From that point on, the network has only one goal: get that cost number as low as humanly, or I guess machinely, possible. But doing that, well, that presents a truly mind-boggling challenge. And that brings us to what you could call the million knob problem, or more accurately, the billion knob problem. Imagine you're trying to tune a super complex machine, but instead of a few dials, you've got billions of tiny interconnected adjustment knobs. That's exactly the situation a neural network is in every time it needs to learn. Just look at that number. A big network like GPT-3 has hundreds of billions of these things, these adjustable parameters. Every single one contributes in some small, almost imperceptible way to the final answer. So when the network messes up, it has this impossible task. Which of these billions of knobs do I turn, and which way do I turn them to get a better answer next time?
So what are these knobs? Well, they're called weights and biases. A weight basically decides how strong the connection is between two brain cells, or neurons, in the network. A bias, on the other hand, is kind of like a neuron's own personal thumb on the scale. It makes it just a little more or a little less likely to fire. At the end of the day, learning is really just the long, complicated process of finding the perfect settings for all of these knobs.
Okay, so how in the world does the network find the right settings? It's not just random guessing, that would take forever. Instead, it uses this really clever strategy called gradient descent, which is all about one thing: finding the fastest way downhill to reduce its error. I want you to picture the cost function as a giant, sprawling landscape full of hills and deep valleys. The height of the ground at any given point represents how big the network's error is. So the network's one and only goal is to get to the absolute lowest point in that entire landscape, the point where the error is as close to zero as possible.
The whole process works just like a hiker trying to get to the bottom of a valley on a really foggy day. First, the network makes its guess. Then it checks its error. That's like checking its altitude to see how high up the hill it is. Next, right where it's standing, it feels around for the steepest downhill slope. And finally, it takes one small step in that direction. Then it just does it all over again, and again, and again, until it finds the valley floor. And of course, this brings us right back to our billion knob problem. Finding that downhill direction, what the math folks call the gradient, that is the whole ballgame. If you tried to do it the simple, naive way, you'd have to physically wiggle each one of those billions of knobs, one by one, just to see how it affected the error. I mean, that's not just slow, it's computationally impossible.
And this, right here, is where the absolute genius of backpropagation comes into play. It is an unbelievably efficient way to calculate that downhill direction for all the knobs all at once. And it does it by, you guessed it, working backwards.
I mean, just look at the difference here. The naive way, on the left, it's a complete brute force nightmare. You're checking every single possibility. But backpropagation, on the right, it's just so elegant. It only needs one trip forward through the network to see the mistake, and then one trip backward to figure out how every single knob contributed to it. 2 passes. That's it.
And we're not talking about a small improvement here. For a network with 1 million weights, this is about 500,000 times faster. This isn't just a little optimization. This is the difference between deep learning being a cool idea in a textbook and a technology that is actively changing our world.
So how does this magical backward pass actually work? Well, the best way to wrap your head around it is to think of it like a detective story. The whole point is to assign blame for the mistake.
As Michael Nielsen puts it so well, backpropagation is all about calculating this thing called a partial derivative. Now that's just a fancy math term for measuring how sensitive the final error is to a tiny little tweak in each specific knob. It's how the network figures out which knobs are the most responsible for the mistake.
So here's the key idea. That final error, that wrong answer, that's the crime scene. Our detective, backpropagation, starts right there.
Its job is to trace the evidence backward from that scene, figuring out exactly how much blame to assign to every single neuron and connection that led to that bad outcome. And this investigation is incredibly systematic. The detective starts with the output neurons, the ones that made the final wrong call, and calculates their direct blame. Then it takes a step back to the layer right before it and asks, okay, you guys, how much did each of you contribute to that final mess? And it just keeps doing this, working its way backward, layer by layer, all the way to the beginning. Now, under the hood, this whole detective process is run by 4 core mathematical equations. We don't need to get into the nitty-gritty math, but this table gives you the gist of what each one does in our story. BP1 starts the case at the crime scene. BP2 traces the blame backward to the earlier suspects. And BP3 and BP4, they're the ones that finally connect that blame to the individual knobs, the weights and biases, so they can finally be adjusted correctly.
So, this incredibly elegant, super efficient method for assigning blame and correcting mistakes, that is precisely why backpropagation has had such a truly monumental impact on the world of AI. What's wild is that the algorithm was actually floating around back in the 70s, but its real power wasn't understood until this landmark paper in 1986 came out and showed the world just how fast it was. That paper basically lit a match, but it took the insane computing power of the 2010s for that fire to turn into the deep learning inferno that we're all living in today.
And the authors of that 86 paper, they really didn't mince words. They knew they had stumbled upon a key that could unlock problems that, up until that point, were thought to be completely impossible to solve. And you know what? They were absolutely right.
So, if you take one thing away from this, let it be this. Backpropagation isn't just some clever piece of code. It's the fundamental engine that makes learning practical for networks with millions or even billions of moving parts. It is the reason AI can learn to see, to hear, and to create in all the incredible ways that we're seeing today.
And that leaves us with one last, pretty fascinating question to ponder. This incredibly powerful method of learning from error has already transformed our world. So as it gets even better and faster and more efficient, what new, once impossible problems will it learn to solve next?